Let's do a couple more examples. This time, I'm not going to spend a lot of time on it. I'm just going to talk you through a few of these. So, as we take limits and kind of what they look like. So, you can copy this down and try it on your own if you'd like. And then you can come back and look at the solution. So, I have that and another couple down here, but I'm not going to spend as much time going through them. We'll spend time in the problem sessions and do a couple more of these. So we want to look at the square root of 9x squared plus 2 over 4x plus 3 as our function. And we want to see what happens to f of x as x approaches infinity and negative infinity. One of the critical things we're going to use when you do this one is the square root of x squared. So that's you can define that basically as the absolute value of x. So the square root of x squared is essentially the absolute value of x. So if x is positive, then it's just x. But if you have the square root of x squared, that's the absolute value of x, and x is negative, then it's negative x, right? Because if x is a negative value, you would interpret that as a negative negative, which makes it positive. So that's what we're going to use a little farther down. So when you do this, simplify this thing, the highest power is x. And so you are going to go through, well, no, actually what I did first here is I'm simplifying this. So I'm rearranging it essentially to take out an x. So see what I did here? So if you distribute this x squared back, you get 9x squared plus 2. So in that form, I can then rewrite this as root x squared root 9 plus 2 over x squared. So that right there tells me what I can do. So in the case A, this is approaching positive infinity. So this is actually the root x squared would need to be just positive x. Okay, then you do the same process, multiply by 1 over x, and this is gone, and then this goes to 0, and this goes to 0. And so you end up with just 3/4. Now the next case, the middle is the same, but when you take out the square root of x squared and you're approaching negative infinity, then now you're in this situation and you would need to write it as a negative x. That's why I did this one, basically. Similar homework questions. And so when you do that, you get the negative 3/4. All the rest of it is the same. Okay, so this one's not, simple. This one takes a little bit of work to look through it and think about it. Find one similar in the book and try another one that's like this. Okay. Next one, another sandwich theorem. So let's just talk about the explanation here. So we're looking at sine x over x. We're not approaching 0, we're approaching infinity. So we know sine x oscillates between -1 and 1, right? So the limit of sine x as x approaches infinity just oscillates. So the limit doesn't exist. It does not approach anything. It doesn't approach infinity, doesn't approach a specific number. It just oscillates like that. Well, it's symmetric, but all right. So then if you use squeeze theorem, you can come in here and write your inequality that we know is true about sine, and then we divide everything by x. And so negative 1 over x goes to 0, 1 over x goes to 0 as you approach infinity. So that means this middle must also go to 0. So therefore, by the squeeze theorem, that limit of sine x over x as x approaches infinity must also equal 0 by this squeeze theorem, or sandwich theorem as the book uses. So it oscillates, and you can graph those things. It oscillates, and then so it goes like this, and then it gets bigger, and then it like that. You can see what that graph looks like. Okay, this next one is kind of introducing some rational function stuff again. That limit as you approach 2 on the right. Now I actually, it looks like when I did this, I graphed the whole thing. So we'll spend some more time on this one. So don't worry about it too much. But what happens as you approach 2 on the right? Because 2 is, right, this is all reduced. Everything's nothing to cancel out or simplify. So x equals 2, which would be this line here, is a vertical asymptote. So we call those the VAs. So vertical asymptote at x equals 2. What happens as you approach on the right? Okay, and then you can interpret this thing of what to do. You can see that, and it's I didn't do it down here, but we can do it actually. So if we do that limit x plus 3, x minus 2, x plus 1, and you're approaching 2 on the right, so like 2.1. So basically how you can interpret this thing is the top will be positive, and then what's this going to be? Is that going to be a positive number or a negative number? If you approach 2 on the right, it'll be a positive number. And then if you put in a 2 here, it's also positive. So this is a positive divided by all these positives is going to make a positive. But you know that this value here in the denominator, this is going to 0. So this whole thing will be going to positive infinity. And if you look at the graph, that's exactly what I have here. It goes to positive infinity. Same arguments as you approach -1. That's here, -1 on the left. Okay, so if you push negative on the left, then you got a negative, negative, positive. So the whole thing is going to positive. So -1 on the left, again, is going up. Okay, so we'll talk more about this one as we do. We're going to be graphing those a little bit when we get into graphing functions using derivatives and all that stuff we'll be defining later. Okay, so these are just ones to take a look at and look at similar ones that the book has. So that wraps up chapter 2. We will go on to chapter 3 next and get into the definition of derivative.